December 17, 1944. Frozen fields outside Stavelot, Belgium. The Panzerfaust round struck Technical Sergeant Michael Donovan's Sherman at a 40-degree angle, penetrating the lower hull with a sound like tearing metal. Inside the tank, time fractured into milliseconds. Donovan, commanding from the tank commander's position, felt the concussive wave before hearing the explosion. The German Volksgrenadier who fired the shape-charge weapon was already reloading, expecting the customary fountain of flame that marked a successful Sherman kill. He never got to fire that second round. Donovan's gunner, Corporal James Webb, put a 76mm round through the snow-covered hedge where the German soldier crouched. But what the German never understood, what he would never live to report, was why that first hit didn't immolate 5 American tankers in an instant inferno. 22 months earlier, a modification had been welded into that Sherman's hull floor. The German soldier, his squad, his company, his entire army would fight the rest of the war without knowing it existed. May 28, 1943. Beaune, Algeria. Captain Richard Hayes of the U.S. Army Ordnance Department walked through a field of burned-out American armor with a clipboard and a sick feeling in his stomach. The Battle of Kasserine Pass had ended 3 months prior, but its lessons were still being documented. Hayes counted his 64th destroyed Sherman of the day. The interior was carbonized black, the aluminum fittings melted into pools, the steel bulkheads warped from temperatures exceeding 2,000 degrees. He knew what had killed the crew. Not the German shell that penetrated, that had struck the sponson above the right track, punching through 17 millimeters of armor. What killed them was the 75mm ammunition stored in vertical racks along that exact wall. 47 rounds of high-explosive and armor-piercing ammunition, each containing enough propellant to launch a 16-pound projectile at 2,000 feet per second. When the German shell fragmented inside the fighting compartment, superheated steel splinters ignited the exposed powder charges. The crew had perhaps 3 seconds before the chain reaction became unstoppable. The driver, technician 5th grade Robert Morrison from Buffalo, died in his seat, trapped by the transmission housing. The assistant driver never reached his hull escape hatch. The turret crew, commander, gunner, loader, were found in positions suggesting they'd tried to bail out through the top hatches. The thermal bloom had caught them halfway. Captain Hayes had examined 97 destroyed Shermans that week. 74 had burned completely. His preliminary report to the Ordnance Department Tank Automotive Center was stark: current ammunition stowage configurations present catastrophic fire hazard. Crew survivability after penetrating hit estimated at less than 20%. Immediate remedial action required. That report landed on the desk of Colonel James Cummings at the Detroit Arsenal on June 3, 1943. Cummings, a mechanical engineer before the war, had designed automotive cooling systems. He understood heat transfer, fluid dynamics, and the properties of liquids under stress. He read Hayes' report 3 times, then called a meeting. The conference room at the Detroit Arsenal on June 8, 1943, contained 12 men representing ordnance, engineering, and battlefield analysis. Cummings opened with Hayes' findings. "Gentlemen, we are losing 4 out of 5 penetrated Shermans to ammunition fires. The Germans know this. They're specifically targeting our ammunition storage areas. We need a solution that can be implemented in current production without completely redesigning the tank." The discussion lasted 4 hours. Initial proposals were impractical. Complete relocation of ammunition to the hull floor would require redesigning the turret basket, transmission, and driver compartment, a 6-month engineering nightmare that would halt production. Armoring the ammunition racks more heavily would add unacceptable weight. Using less volatile propellant would reduce gun performance. Then someone suggested water. The initial idea was dismissed as absurd. Filling the fighting compartment with water would create impossible working conditions. But Dr. William Spence, a chemical engineer from DuPont attending as a consultant, refined the concept. Not surrounding the crew with water. Surrounding the ammunition. Double-walled containers with liquid in the interstitial space. When a shell fragment penetrates, the liquid floods out, cooling any exposed propellant below ignition temperature before the fire can spread. The concept was elegant. The engineering would be brutal. Cummings assigned a team of 6 engineers to develop a prototype. They had 3 weeks. By June 30, 1943, the team had fabricated a mock-up system. 10 rounds of 75mm ammunition were housed in a double-walled steel container measuring 14 inches wide, 22 inches long, and 6 inches deep. The walls were separated by a 1.5-inch gap filled with 4 gallons of water. On July 2, at Aberdeen Proving Ground in Maryland, technicians placed the prototype in a test fixture and fired a German 75mm armor-piercing round at it from 30 meters. The shell penetrated both walls. Water gushed out, flooding the ammunition compartment. A small fire ignited in one propellant charge where fragments had directly struck it, but the flame extinguished within 4 seconds as water continued flowing. The propellant smoldered but never achieved sustained combustion. Technicians repeated the test 6 times with captured German 88mm rounds. 4 tests resulted in brief fires that self-extinguished. 2 tests showed no ignition at all. The data was undeniable. Traditional dry ammunition storage ignited in 73% of penetrating hits. Wet storage burned in only 15% of cases, and even those fires were controllable rather than catastrophic. On July 15, 1943, the Ordnance Department authorized full development of what would officially be designated the Wet Stowage Ammunition System. The goal was to have production models ready by January 1944. That gave engineers 6 months to solve a dozen problems. Pure water froze in winter, rendering the system useless in northern European cold. Initial field tests in refrigerated chambers showed solid ice at temperatures below 28 degrees Fahrenheit. Adding ethylene glycol prevented freezing but accelerated corrosion of brass cartridge cases, ruining ammunition within weeks. The final solution came from industrial chemistry, a mixture designated Ammudamp, ethyl sodium potassium phosphate with rust inhibitors and biocides. This compound remained liquid to -40 degrees, prevented corrosion, inhibited bacterial growth in stagnant liquid, and actually improved fire suppression properties compared to pure water. Each wet stowage bin required precision manufacturing. Inner and outer steel shells were press-fitted with exact tolerances to maintain the 1.5-inch gap. Drain plugs, inspection ports, and filling valves had to be leak-proof under combat conditions including artillery concussion, rough terrain impact, and temperature extremes from Sahara heat to Russian winter. By September 1943, Press Steel Car Company in Pennsylvania was retooling its Sherman assembly line. The modifications were comprehensive. The hull floor needed complete redesign to accept ammunition bins below the turret basket. This required new stamping dies, modified welding jigs, altered assembly sequences, and rerouted hydraulic lines, electrical cables, and control linkages. The full turret basket had to be replaced with a partial rotating floor to allow crew access to hull ammunition. This meant redesigning the turret traverse mechanism and rebalancing weight distribution. Engineers worked 16-hour shifts through autumn. On January 3, 1944, the first M4A1-70-6W rolled off the press steel line. The W designation stood for wet, though few beyond factory floors understood its significance. The tank weighed 900 pounds more than standard models due to the liquid-filled bins and reinforced hull floor. It carried 71 rounds of 76mm ammunition in floor storage plus 4 ready rounds in the turret, protected by 36.6 gallons of Ammudamp solution. Production ramped up immediately. Fisher Tank Arsenal in Grand Blanc, Michigan, transitioned to M4A3-70-5W production in February. By March, both factories were producing exclusively wet stowage variants. Every Sherman rolling off American assembly lines now contained the modification. German intelligence had no idea. While American factories revolutionized tank survivability, German technical analysis remained frozen in 1943. The intelligence failure had structural roots that would prove catastrophic. Kummersdorf Proving Ground, 40 kilometers south of Berlin, January 1943. Waffenamt technical specialists were conducting detailed analysis of an M4A1 Sherman captured intact at Kasserine Pass. The evaluation took 3 weeks and was extraordinarily thorough. German engineers measured every component, tested armor composition, evaluated engine performance, analyzed transmission characteristics, and meticulously documented ammunition storage. Their findings were compiled into a comprehensive technical manual distributed to all panzer units. The ammunition storage section included detailed drawings showing vertical racks and sponsons above the track level, with specific recommendations: primary kill zone, right sponson, ammunition storage area. Secondary kill zone, left sponson, ammunition storage. Penetrating hits to these areas will result in catastrophic ammunition fire in 70 to 85% of cases. Prioritize these target areas for maximum effect. This assessment was accurate for the tank they had captured. It would remain German doctrine for the next 2 years, even as every Sherman they faced had been fundamentally changed. The intelligence breakdown had multiple causes. Organizational fragmentation meant German technical analysis was divided among competing agencies, Waffenamt, Heereswaffenamt, various SS technical branches, with poor information sharing. Resource constraints meant captured vehicles went immediately into combat service rather than systematic evaluation. Cultural overconfidence in German technical superiority reduced perceived need for continuous enemy equipment analysis. But the deepest cause was temporal. The German evaluation occurred using specimens captured before the modification existed. By the time Wet Stowage Shermans entered combat, German forces had shifted to defensive operations with limited opportunity for systematic technical intelligence. Frontline reports of unusual Sherman survivability were dismissed by staff officers as exaggerations from combat-stressed troops. Every subsequent intelligence update referenced the Kummersdorf evaluation as definitive. When panzer crews reported achieving penetrations without fires, they assumed they had simply missed the ammunition racks. The idea that Americans had solved the fire problem never appeared in German intelligence assessments. Gunnery schools from Putlos to Paderborn taught students to target Sherman sponsons. Range cards issued to anti-tank units highlighted these areas in red. The tactical doctrine was embedded so thoroughly that even when sponson hits stopped producing fires, crews doubled down on the technique, assuming they needed better shot placement. The modification that would save 5,000 American lives succeeded partly through engineering excellence, but equally through enemy ignorance. April 1944. Tidworth Barracks, England. Technical Sergeant Michael Donovan, newly arrived with the 3rd Armored Division, walked around his assigned Sherman for the first time. The M4A3-70-6W looked externally identical to the Shermans he had trained on at Fort Knox. Same profile, same armor, same road wheels. His crew chief, Staff Sergeant Albert Chin, pointed to inspection ports on the whole floor. New ammunition system. There's liquid around the rounds. You check the levels every week through these ports. Donovan crouched down, unscrewed an inspection cap, saw amber-colored liquid inside. What's it for? Fire suppression. If we take a penetrating hit to the ammo storage, this liquid is supposed to flood out and prevent the whole tank from burning. Chen's tone suggested he was repeating information from a manual he did not quite believe. Donovan replaced the cap. In 6 months of combat ahead, he would never think about those liquid-filled bins again. Not until the Panzerfaust hit outside Stavelot would he realize what they had saved him from. The 3rd Armored Division completed training through June. By July, 104 of their Shermans were M4A3-70-6W variants with wet stowage. Not a single soldier in the division understood the historical significance of what they were about to deploy. On July 25, 1944, Operation Cobra commenced. At 09:38 hours, the heaviest tactical air bombardment in history pulverized German positions southwest of St. Lo. 2,500 bombers dropped 4,000 tons of high explosive on a rectangle measuring 5 kilometers by 1.5 kilometers. As smoke cleared, American armor surged forward. Donovan's tank company led the assault. 2nd Panzer Division, devastated by bombardment, positioned surviving Panthers in ambush along hedgerows. At 11:40 hours, Donovan's tank crested a slight rise and took fire from a Panther 700 meters distant. The German gunner was skilled. His first shot struck Donovan's Sherman on the frontal slope at a sharp angle, deflecting without penetration. The second shot, fired 3 seconds later, hit the right sponson squarely. The armor-piercing round punched through 17 millimeters of side armor and fragmented inside the crew compartment. Donovan felt the impact through his feet, heard the characteristic ringing shriek of spalling metal. His gunner, Corporal Webb, was already traversing toward the Panther's position. Donovan expected fire, expected heat, expected the explosive death he had been trained to fear. Instead, he heard liquid rushing, smelled a sharp chemical odor, and saw amber fluid pooling on the turret floor. The ammunition bins below had been penetrated. Liquid gushed out, soaking the rounds, cooling metal fragments before they could ignite propellant. Small flames flickered in one bin, then extinguished as more liquid flowed. Webb fired. The Panther's front slope deflected the round, but the German crew, seeing a Sherman still fighting after achieving a clean sponson penetration, withdrew in confusion. Donovan's Sherman limped to a maintenance area. Inspections revealed the penetration had struck directly into a wet stowage bin holding 12 rounds. 4 rounds showed scorching. None had detonated. The tank was back in service within 18 hours after ammunition replacement and minor repairs. Across the Cobra operational area, German after-action reports reflected growing confusion. Panthers were achieving hits on Shermans at favorable ranges. Penetrations were confirmed. Yet many targets continued fighting or withdrew under power rather than burning. The report suggested American armor quality had improved, or German ammunition was defective. No report suggested the Americans had modified their ammunition storage. 3rd Armored Division advanced 65 kilometers in 4 days, maintaining momentum despite repeated engagements. German defensive calculations, based on expected Sherman attrition rates, proved inadequate. American tank strength remained higher than German intelligence predicted because tanks that should have burned completely were being repaired and returned to combat. September 19, 1944. Arracourt, France. The 113th Panzer Brigade, a newly formed unit equipped with 80 Panthers, attacked positions held by the U.S. 4th Armored Division. German planning assumed tactical surprise and superior gunnery would devastate American armor. The initial German assault achieved numerous hits. Panthers firing from ambush positions at ranges between 600 and 1,000 meters scored penetrations on Shermans of Combat Command. German crews reported 12 Sherman kills in the first 30 minutes. The American response defied German expectations. Instead of withdrawing with catastrophic losses, 4th Armored counterattacked with unexpected strength. Shermans that German crews believed destroyed reappeared in fighting positions, returning fire. The reason was mathematical. Of the 12 Shermans struck in the initial German volley, 10 had absorbed penetrating hits. In 1943, 8 to 9 of those tanks would have burned completely, with crews killed or severely wounded. Instead, wet stowage prevented catastrophic fires in 9 cases. 7 tanks were recovered during the day's fighting, repaired overnight, and returned to combat by dawn. The 2 that burned had been hit in engine compartments, gasoline fires unrelated to ammunition storage. German intelligence, counting all 12 as permanent losses, calculated that Combat Command A should be 40% under strength. The actual figure was 12% under strength. When the 113th Panzer Brigade attempted to exploit what they believed was a weakened American position, they met a force nearly 3 times stronger than their estimates predicted. The resulting engagement destroyed the German brigade. 72 Panthers were knocked out over 6 days. American losses were significant, 151 Shermans damaged, but of these, 110 were repaired and returned to service. The mathematical advantage was staggering. A German tank destroyed was a permanent loss, the Reich lacked replacement capacity. An American Sherman penetrated by German fire had an 85% chance of being recoverable if wet stowage prevented fire. American maintenance battalions, working around the clock, transformed tactical setbacks into temporary delays. After Arracourt, General George Patton, initially skeptical of the 76mm gun, reversed his position. Third Army subsequently accepted only 76mm armed wet stowage variants, recognizing that improved firepower plus enhanced survivability created superior combat capability. German forces never understood why American armor strength seemed inexhaustible. Staff officers attributed it to industrial production superiority, which was true, but incomplete. The hidden multiplication factor was tank recovery rates dramatically improved by fire prevention. December 16, 1944. The Ardennes. Germany launched its final desperate offensive in the west, Operation Wacht am Rhein. The assault plan was predicated on destroying American armored reserves through concentrated panzer attacks. German planning calculations assumed traditional Sherman vulnerability. Staff estimates predicted that for every 10 Shermans engaged and penetrated at favorable ranges, 7 to 8 would be permanent losses to fire. Operational timelines were built on these projections. When Kampfgruppe paper, spearheading 1st SS Panzer Division's assault, encountered American armor near Stavelot on December 17, the calculations began failing. Donovan's Sherman was with the 3rd Armored Units rushed to contain the German breakthrough. That was when the Panzerfaust struck. The shaped charge warhead, designed to defeat heavy armor, penetrated the lower hull. Normally, the jet of superheated gas and molten metal would ignite anything flammable. Donovan's ammunition bins were directly in the penetration path. Liquid flooded the crew compartment. The temperature inside spiked momentarily, then dropped as Ammudamp solution vaporized, absorbing thermal energy. Small fires started in 2 rounds where the jet had directly contacted propellant, but both extinguished within seconds. Donovan's crew bailed out, expecting imminent explosion. They lay in frozen mud for 30 seconds, waiting for the detonation. It never came. An hour later, maintenance crews inspected the tank. The penetration was clean, the hull compromised, but the ammunition storage intact. The tank was towed to a repair depot, received a welded hull patch, fresh ammunition bins, and was back in service within 4 days. Across the Ardennes battlefield, this pattern repeated. German forces achieved tactical surprise and initial success, but American armored units maintained cohesion at rates German planners had not anticipated. The 743rd Tank Battalion absorbed repeated attacks near Stavelot. Despite suffering numerous penetrations, the battalion maintained operational effectiveness throughout the 6-day battle. German commanders expressed frustration in war diaries. SS Obersturmbannführer Joachim Paper, in post-war interrogations, noted American tanks continuing to fight after hits that should have destroyed them. He attributed it to American determination and superior numbers, never recognizing the engineering modification that had changed the equation. By January 1945, German forces were in full retreat. The Bulge offensive had failed partly due to fuel shortages, partly due to Allied air superiority once weather cleared, but significantly due to miscalculations about American armored strength sustainability. Every German operational plan had used obsolete vulnerability data. This systematic error, repeated across thousands of engagements, accumulated into strategic failure. March 1945. The Rhine. American forces were driving into Germany. Donovan's Sherman, repaired after Stavelot, bore scorch marks and welded patches from 4 separate engagements. His crew had survived direct hits on 3 occasions. Only once did Donovan consciously recognize what had saved them, reviewing the maintenance log after Stavelot, seeing, Wet Stowage System intact, functioned as designed. The vast majority of tank crews never made that connection. The system worked invisibly, its success measured in fires that never happened, in crews who walked away from penetrations that should have killed them. By April 1945, American forces were capturing dozens of German-operated Shermans. Some had been pressed into German service after capture at the Bulge. Wehrmacht and SS crews operated these vehicles for weeks without noticing the liquid-filled ammunition bins. Even when maintenance was required, German mechanics drained and refilled the bins without understanding their purpose. The modification that had saved thousands of American lives remained undetected by enemy forces up to the war's final weeks. The intelligence failure's scope would only become clear post-war. June 1946. U.S. Army Operations Research Office, Bethesda, Maryland. Analysts were compiling comprehensive assessments of tank warfare in Europe. Their statistical analysis, later published as Report ORO-T-117, documented the transformation. Pre-modification Shermans, 60 to 80% burn rate after penetrating hit. Wet stowage variants, 10 to 15% burn rate. Crew survivability increased from less than 20% to over 65%. Conservative estimates suggested the modification prevented catastrophic fires in at least 1,000 tanks, representing 5,000 trained crew members saved and dozens of battalions maintaining combat effectiveness instead of requiring reconstitution. Researchers cross-referenced German documents captured during occupation. Not a single after-action report, intelligence briefing, or technical analysis mentioned recognition of improved Sherman fire resistance. Post-war interviews with German tank commanders confirmed the blind spot. Otto Carius, who destroyed over 150 enemy tanks, wrote extensively about fighting Shermans without noting unusual fire behavior. Ernst Barkmann's detailed memoir contained no mention of Sherman survivability changes. Unit histories compiled by veteran associations showed the same gap. Histories of Panzer Lehr, 2nd SS Panzer Division, 116th Panzer Division contained no recognition of the modification. These were private recollections among former comrades, not official documents subject to censorship. The absence was genuine. American interrogators specifically asked German tank commanders about Sherman vulnerabilities. Responses consistently referenced ammunition fires as the primary method of achieving kills, with no indication they had noticed a change. The wet stowage modification represented one of the most complete intelligence failures in modern warfare. A fundamental change to enemy equipment, deployed across thousands of vehicles, engaged in hundreds of battles, captured and operated by enemy forces, yet remaining completely undetected for the war's final year. Technical Sergeant Michael Donovan mustered out in November 1945. He returned to Cleveland, married his fiancée, and worked as a machinist for 32 years. In 1977, at a 3rd Armored Division reunion, someone mentioned wet stowage. Donovan, who had survived 4 penetrating hits during the war, learned for the first time the specific system that had saved his life. He was 61 years old. The realization that his survival had been engineered into the tank, not luck, not divine intervention, but deliberate human design, moved him deeply. He wrote a letter to the Aberdeen Proving Ground archives, thanking engineers whose names he would never know. The wet stowage system remained standard in American tank design through the Korean War. Later vehicles used improved fire suppression systems building on the same principles: isolate propellant, prevent ignition spread, give crews survivable margins after penetration. For military historians, the modification offers enduring lessons. Technical intelligence requires continuous updating. Yesterday's enemy may not be today's. Innovations need not be revolutionary to be decisive. Evolutionary improvements solving specific problems often prove more valuable than dramatic redesigns. For intelligence services, cautionary lessons about analytical blind spots, the capability that seems impossible may prove decisive. In warfare, information equals ammunition. For engineers, validation of practical design philosophy: identify problems, develop deployable solutions, implement immediately. The modification achievable now trumps the perfect solution requiring years. The Sherman tank wet stowage ammunition system reduced catastrophic fire probability by 75%. It saved thousands of lives. Its greatest success was remaining invisible to German forces throughout the war's crucial final year. American engineers designed it to save lives, not deceive enemies. Yet invisibility multiplied effectiveness beyond calculation. History records wet stowage as crucial technical improvement. More accurately, it should be remembered as the modification that won by remaining hidden, achieving victory through enemy ignorance as much as American engineering. German tank crews fought obsolete tactics based on faulty assumptions. They lost. The modification did not just save American lives. It shortened the war by maintaining American armored strength at levels that accelerated German collapse. In warfare, we celebrate visible triumphs, the new weapon, the bold strategy, the dramatic breakthrough. But history's most decisive advantages are often invisible. Wet stowage won not through superiority but through enemy blindness. It saved lives not by preventing hits but by preventing consequences. It shortened war not by destroying enemies but by sustaining allies. Perhaps the deepest lesson, sometimes the battle you win is the one your enemy never knew you were fighting. Technical Sergeant Donovan understood this only decades later. The liquid that saved him in frozen Belgian fields was 36 gallons of engineered chemistry that German intelligence never saw. 5,000 men came home because of it. Most never knew why. That invisibility was the ultimate victory.